right, let's start on time. Today we're going to talk about this so-called combinational building blocks. You guys remember some of the discussions in the very first lecture. We were talking about how to tackle the complexity, right, of this modern day digital system, right? So where we have billion transistors. One of the key approaches that we mentioned is so-called the bottom-up approach, right? So where we build up layers of abstraction, right? So that we can use the building block, right, in a lower layer, and then use them to form more complex building blocks, right, in another layer. And then we keep doing this. So today we are going to see, we're going to see some flavor of this, right? So using this conditional logic. And also last time we already talked about, right, so how to build gates, right, using CMOS logic. All right, so cool announcement. Okay, first lab 2 is due today, right? Midnight today. In case you're behind your schedule, just want to remind you that you are allowed to submit slip day requests. Right? Make sure you read the syllabus so that you can understand the procedure. Okay, you only get to use the slip days twice, and you have 7 slip days in total. Okay. Yes, sorry. Typo there. Lab 1. Okay. Good catch, guys. So lab 1. We are going to post lab 2 this week as well. That's probably why I made this a typo. And we are going to post homework 2 tonight. Okay, so that's not a typo. Okay. All right, so before I talk about the new content, right, so let's review some of the things that we covered last time. Okay, so where we talked about CMOS logic, right? Let's just do, just like last a week ago, right? So let's just go to item pool. Okay. I have a few questions for you guys. Okay, let me share the other screen. All right. So I just want to help you guys refresh your mind about some of the key concepts that we covered last time. If this is a multi-choice question, you can check more than one options. We'll move on in about 20 seconds. Guys, asking you about like which ones are not true. Right. Answers are rolling in. Okay, I'm going to review the solutions. It looks like we have some, most people are agreeing. Okay. We are reaching some consensus. Okay. All right, so let's see, right? So first statement, is it true or false? True, right? Second one, and let me just review the answer. Second one, PMOS network cannot pass right? So pass is a poor one. That's a false statement, right? PMOS network cannot pass a good 0. So PMOS network is also called a pull-up network, right? Remember the term from last time? So actually connected to the VDD, the high voltage, right? So that's where we use PMOS network to pass a 1. NMOS network cannot pass a good 1. Okay, and third one is true, right? We talk about 3 input NAND, 6 transistors, right? 3 NMOS, right? 3 PMOS. And NMOS is active high, right? So the reason I want to include this option is I want to make sure you guys know this term, right? When we say active low, usually we have a bubble, right? PMOS has a bubble, right, in the symbol. So PMOS is active low, not NMOS. And CMOS gate, we're talking about static CMOS gate, right? So we always have even number of transistors, right? Because we have the same number of outputs. So the number of PMOS and number of NMOS, they are the same, right? They're equivalent. So we always have an even number of them. Okay, looks like most of you got it right, which is great. And some of you think that A is also incorrect, right? So if NMOS network and PMOS network, they are on at the same time, then we have something called a short circuit, right? They cannot be on at the same time. Okay, next question. What is this gate? Don't construct a truth table. Write down expression. Try to write down expression by analyzing either PMOS network or NMOS network. So I'm gonna soon start to switch to a second screen so I get to see the chat window. Right, so what ends? I'm gonna review answer. Pretty soon. All right, this is not a quiz, right? So we are just doing exercise. Yeah, when we are doing a quiz, I'm gonna let you know. This is just meant to help you refresh your mind. What is the gate? It's basically, actually this diagram is the same, right? The CMOS diagram is the same with what you did for the last lecture, right? So we did a quiz in the last lecture, the same diagram, right? So actually, that mystery gate is basically a NOR, right? So this is a NOR. Why is this a NOR? How do we analyze this? So we can just look at this parallel structure, right? In the pull down network or the NMOS network, and then we can just write down the expression, right? Since it's parallel, we have an OR, right? So just look at the inputs, right? So we have, there's a parallel, so basically A plus B, but we are not done yet, right? Since we are analyzing the NMOS network, we need to invert it, right? So this is basically a NOR gate. And we can also analyze, right? So from the top, right? So this is the PMOS network, or pull-up network. So this is in series, right? We have something called series subnet. So this is where we have AND, right? But since we have active low PMOS, so we do A naught and B naught. This is also a NOR, right? According to De Morgan. Make sense? Okay. Right. And also this is the solution, right? For the quiz from last time. Last time I asked you guys to enter the basically the output, some of the missing entries in the output column for this CMOS gate. In case of question, feel free to ask. All right. Okay. Any questions about this? If not, let's move on. I think there's some additional question on chat window about homework, right? So we are going to post homework. Homework 2 is going to be due next Friday. Right? Homework 1, indeed, is going to be due this Friday. All right. Okay, I also show you guys this gate, right? So last time at the very end, I just want to discuss this a little bit more. This is actually AND gate, right? So I just want to make sure that you guys pay attention to this connection, right over here. Okay, this connection. So this is where we are sort of concatenating, right? So we are connecting two CMOS gates. The first one is a NAND gate, right? On the left, we have a NAND gate, and on the right, we have an inverter. So in this case, this connection basically connects the output of the NAND to the input of the inverter, right? So this is an AND gate. That's how we construct an AND gate. And the reason we want to talk about this is because I really want to convince you that indeed NAND and NOR, they are actually more efficient, right, in terms of the CMOS implementation. So that's why we care for them, right? Because these CMOS gates, we will look at this behavior of the CMOS, right? They have sort of this inverting behavior, right? Inherent, they have this inherent inverting behavior, right? So think about this inverter, right? Over here, so if this path is connected, right, or conducting, so we right, so we basically input 0 and output is high, right? So basically we put it up. And because of the inverting behavior, it's actually more natural, right, to use it to build something like NAND or NOR. Okay? And for AND gate, we actually need to spend additional transistors. In this case, 2 more transistors. Okay, so this is CMOS, right? And let's come back to this gate level abstraction, right? Like I mentioned last time, we'll only take a quick look, right, at the CMOS, right, which is slightly below this gate level abstraction. Let's come back to the gate level thing. Okay, and this is another quiz that you guys did last week, I believe, right? So this is I think this is a quiz from last Thursday, right? Ask you guys to do kernel map, right, for this specific 2-level for this specific function for 2-level logic implementation. How many circles do we need? You guys may not remember the answer anymore, but just quickly looking at the kernel map, how many? 2, right? Okay, many of you got it right. So if we are doing this canonical sum, right, we are trying to minimize the SOP form. First, right, for kernel map, we pay attention to the things on the corner, right? So these 2 corners, they are indeed adjacent, right? So it's really important to understand the concept of adjacency for kernel map or K-map. And we circle this column, right? That's it. So we only need 2 circles or 2, the so-called prime impedance to cover all the ones. Okay, and you look at this, right? So we start out with a problem statement, right? And then we derive the truth table. Then we can also derive this canonical sum, right? In many cases, right, this canonical sum is going to be simpler than the truth table, right? Since we either just look at the ones or zeros, right? Onset or offset. But in many cases, it may not be simple enough, right? So that's where we try to further simplify it, right? Using K-map, all these Boolean algebra theorems. Okay. But just want to quickly make a note here. It is actually an important note. So kernel map is actually a tool for human designers, right? And we mostly use it for minimizing the simple functions, right? Like in this case, we only have 3 input, 1 output function. If you indeed have many inputs, later on you guys are going to construct circuit like that. So you guys going to construct a much more complicated circuit using Verilog. Okay, that is a Howard string language later on, and using Cordis. That's why you guys are installing the tool. We will have a much more complicated conditional logic. So kernel map will not be that effective. Just think about it, right? So the moment you go above 4 inputs, so it's going to be pretty complicated, right? The textbook has some section talking about how to do the 5 input, 6 input kernel maps. So there, really what we are doing is that we're constructing like three-dimensional, right, map. Think about the spatial mapping, right, spatial encoding, and then project them to the 2D space, 2D plane. Okay, so this is really not that very productive. Okay, so that's why in most cases, right, for simple logic, we can do 2-level minimization or 2-level form. But for more complex logic, so we actually want to use this so-called multi-level logic form. This is something that I briefly mentioned, right, last week. So basically with multi-level logic, we are not really limiting ourselves, right, to this SOP or POS form. So instead, we can construct multiple logic, right? So in this case, this is not really a 2-level logic form, right? We have 1 level, 2nd level, right, 3rd level, right? We can have arbitrary number of levels, right? Depending on how complex the circuit is, right? What is the timing constraint, which is something that we're going to discuss pretty soon. And if you look at this circuit diagram, it's actually pretty easy to parse, right? What exactly this diagram is doing. So we just need to trace the inputs, right? So we can just, this is input size, we can just read it off, right? So we can just read off the the intermediate signals, right? So this is basically A or B, right? This is C or D, right? And this guy is basically A plus B and C plus. I have some inversion here. This is C naught, right? C naught. Okay, right. In the end, we have something like this, right? If you guys don't believe me, right, you can try to expand it, right? Expand Y into two-level form. So you will see you indeed need more gates than the multi-level form. Okay? This actually is just a simple example. I'm going to show you another extreme case. Okay? So where we actually need even more gates for two-level form. All right, so one thing to note is actually multi-level logic, right? So this form is not canonical, right? So, you know, for the same function, we may have different kind of circuit diagrams. We may arrange it in many different ways. And, you know, in some cases, right, one way, right? So one of the arrangement of organization of the multi-level logic will be more efficient than others. So this actually turns out to be a fairly interesting and fairly complex optimization problem. So this is usually where we rely on the computer-aided design tools or CAD tools. Okay, so basically optimizing the multi-level logic itself is a fairly deep topic. So this is not something that we're going to cover in this lecture or in this class. Okay? This is actually studied by another entire research field called logic synthesis. And many of the results from that research field, logic synthesis, so many of the algorithms and many of the automated procedures are implemented in the CAD tool that you're using, which is Quartus. Okay, again, that's why we are using Quartus. And there, you know, Quartus basically, you know, trying to optimize the logic using this multi-level form. Okay, so this is a multi-level logic, right? So today, what we are going to focus on is this so-called computational building blocks. So we're going to be talking about some of the commonly used building blocks. So like comparators, parity check, Mux or multiplexer, decoder, encoder. Okay, so these will be useful later on, right, for us to build more complex systems. Okay, for this lecture, we're going to just introduce them and try to understand the behavior of these building blocks. And in the past, right, actually, this is, I think, probably 20, 30 years ago. So these building blocks are so-called MSI, medium scale integration. Integration means we have tried to integrate, right, so many transistors into this, this sub-module or subsystem. So in the past, called medium scale, but really, we are only talking about tens to hundreds of transistors here. So, so with the modern day chip, so these building blocks are tiny. Okay, we have ton of this kind of building block to form the bigger system today. Okay, so let's start with comparator and parity check. But before that, I actually need to introduce something that you guys probably already know. It's called exclusive OR or XOR. Okay, this is another very commonly used two level. This is actually a two input, right? So let's start with a two input gate, two input, one output. So this is a symbol. Okay, this is XOR. Okay, and the opposite or the complemented one is called XNOR. Okay, so this one is the truth table. This is XOR, and this is XNOR. Okay, just like OR and NOR. Okay. So this is the truth table. What patterns do you guys spot here in the truth table? What is XOR or XOR doing? If you just look at the truth table, can you describe it in a more intuitive way? Alternate, yes. Alternate 0, 1, 1, 0, yes. Good, right. It's basically testing equivalence, right? Many of you spot this pattern, right? Does that make sense? So if you look at the first row, right? Okay, let's just focus on XOR, right? First row, X and Y, they agree with each other, right? Both of them are 0. So for XOR, it's a 0. Okay. Second row, they disagree. When they disagree, when they're not equivalent, XOR is 1. Okay. Third row, same thing. Okay, X and Y, they disagree. We have 1, right? And last row, they are the same. They agree. We have a 0. That's basically what XOR is doing. And XNOR is basically doing the opposite. Right? XOR is basically checking equivalence. So actually, another way to look at this, because later on we can actually generalize it to multiple inputs, not just 2 input. You can do 3 input XOR, 4 input XOR, or 5 input, or n, right? Arbitrary number of XOR. It's not arbitrary number of inputs. So really what XOR is doing is checking. So how many ones do we have in the input combination? So if the number of ones is an odd number, okay, like in this case, right? So we have a single 1 here with odd number, then we have 1. Otherwise, even in this case, we have 2 ones, right? It's an even number, we have a 0. Okay, so this property is also going to be useful, right, later on. All right. Okay, so this is basically the the 2-level form, right? We can just write out the Boolean instruction. This is sort of similar to OR gate, right? Except for one column, one of the entry in the output column. So that's why it's called XOR, and can be used for comparison and error checking. So basically parity checking. So we'll see soon. But let's quickly try to understand a bit more about XOR. So is XOR a universal gate? Last time we talked about this concept, right? So called universal gate. NAND gate is universal, right? We can use it to build anything we want. NOR gate is universal, right? Is XOR universal? How do we use, let's talk about NOT inverter. How do you use XOR to build an inverter? Now we enter A here, right? So we want A prime, right? Just look at the the truth table, right? So we put the 1 here. That's how we build an inverter, right? Clear? Okay. So at least we can use XOR to do inversion. And I'm gonna ask you guys to convince yourself, whether this is universal or not. Try it yourself, whether you can use it to build something else, like OR gate, okay, or AND. I'm not gonna give you the answer. Okay. But let me follow on this, right? With XOR, right? So if we A XOR 1, we have A naught, right? We invert. So can I have this something called the identity element? So what is the identity element for XOR? So what do I want to do this, right? So this is the symbol for XOR. So what do I do if I want to get identity? Very good, 0, right? If you XOR any Boolean variable, right, with 0, you get the same variable. Okay, so this is the identity for XOR. The identity element is 0, right? That's why it's XOR, right? It's actually very similar to OR, right? Same thing for OR. For OR, the identity element is also 0. Make sense? Right? So they're indeed similar. Let me convince you that way. But is there a NAR element? Right? If you think about OR, right? The NAR element, we have something called NAR element, right? Identity, NAR element, right? Think about the Boolean algebra theorem. So the NAR element for OR is 1, right? The NAR element for AND is 0, right? So is there a NAR element for XOR? Yeah, when we talk about this, NAR element, we are talking about a constant, right? Emily, you're right. So XOR with, a variable, right? You can get 0, but that's not really that NAR element. The answer is no, right? So if you look for a constant, right, NAR element. So 1 is not another element of XOR, 0 is not either. Make sense? Okay, there is an identity element for XOR. Okay. So hopefully that convinces you that XOR is indeed different, right, from OR. And this is also related to my question about this universal gate. Right? Yes, again, you guys are right, right? A XOR A is indeed always 0. Okay, but when I refer to the term NAR element or identity element, I'm looking for either 0 or 1, a constant value, not a variable. Right? Okay, so this is XOR, right? XNOR is basically the opposite. Okay, you just need to sort of a complement. Okay, we can actually use XOR to do many interesting things. One is we can use it to do the comparison, right? So in this case, I'm not doing like greater than or less than, so I'm doing like equality check. So for the 2 input, right? There's a comparator, there's an equality checker. Again, if X and Y, we already talked about this, if they're different, right? So we get a 1, right, using XOR. We can also do that for multi-bit inputs. Okay, so we basically do bitwise comparison. So this is where we construct this is a multi-level logic form, right? Okay, we do this. We can do a 4-bit comparator. So in this case, if any one of this, right? So we look at this is basically a 3-input OR, right? A 4-input OR. Sorry, it's a 4-input OR, 2-level 4-input OR. So if any one of this right bit position differs, if any one of this is 1, then in the end, right? So the result is different or 1. Right? Okay, so this is how we can build a comparator using XOR. We can also use it to build something called a parity checker. Over here, I'm just cascading a sequence of XOR gates. So what we are doing here is we want to check. So given a multi-bit inputs, okay, so these are the inputs. So in this case, I have n bits. Okay, right? We can just chain a sequence of cascade a sequence of XOR, and then we can quickly check whether in this n-bit input, how many ones do we have? Not how many. So it's really about do we have odd number of ones or even number of ones. So this is probably called parity. Okay, we can have even parity or odd parity. Okay. So this is actually related to the other property that I mentioned early on, right? So essentially, XOR gate is really a parity checker. So you can actually generalize the definition of XOR into multiple inputs, just like how we can do the same for AND gate and OR gate. Okay, so this is basically the definition for multi-input XOR. If you have odd number of ones, right, in the inputs, then we have 1 on the opposite side. We can do the same for XOR. That make sense? Okay. Right. So very good question. Right. So why is it helpful? Right. So Rushi is asking. Okay. So why do we care about? Right. So then this parity gate. Actually, this is where the so-called error correction logic comes into place. This is actually not in the scope of this this class. But the thing is, this circuits, right? This digital circuit, right, might be subject to some errors, right? So could be case, right? In some cases, 1 bit, right, in the circuit may flip, right? May accidentally flip because of some unexpected conditions, right? Whether it's overheated, or there's something called soft error, right? Basically, there's some particle that hits the circuit. Okay? So that's where we can actually use the parity check to check. So if it's supposed to be, we are supposed to have odd number ones, we can actually encode the value, the Boolean value, in a way that we are supposed to have odd number ones. Okay, if this is indeed happening, then we know there's an error. Okay, again, this is not something that you guys need to know for this class, but this is indeed useful. Right. So, but the reason I want to quickly talk about this parity check is if you look at this this is a multi-level, right? So the multi-level circuit. So we get actually cascaded, right, into many levels. So we can also balance it, right? You can prove that XOR is actually associative and commutative, right? You can also balance this this chain into a tree or something, right? But really, you only need linear number, right? So you only need n, roughly n gates for n input stream, n bit input stream, or n bit input, combination, right? We just need n. But I did something that you guys can check with a small n. So you've actually flattened this logic into two-level form. You're going to end up with a lot of gates. In general, for arbitrary number, let's say n, we actually need to use an exponential number of gates if you have to use a two-level form. Right, so that's where this multi-level logic is really useful. Okay, if you're not convinced, just try it out, for example, 4-input case or 5-input case, and then try to build a truth table yourself, and then try to minimize it. The intuition really is, you think about this truth table, for this kind of parity checking logic, so we will have roughly, think about this truth table, we have 2 to the n, number of entries in the output column, roughly half of them, about basically half of them will be ones and half of them will be 0. So this is actually something that's not too easy to optimize, just think about it. Okay, all right, so this is XOR. Right, so basically you can use the parity to correct errors. Again, this is not something that we are going to talk too much in this class. Okay, this is more important. Okay, more important in this class. This communication block is more important. Okay, for 2300, it's really important. Okay, in general, for digital logic, it's called Mux, multiplexer. Okay, so this is where we actually need to make a choice. Let's say we want to connect one of the n inputs to an output. This is where we have to make a choice. Okay, and Mux is going to be useful for us to make such selection. First, let me try to clarify. I think there's some confusion from lab 1 about resource sharing, how to share wires and segments, So let's say we have an inverter like this, it's okay to have the output. So we have something called output pin, Output of the inverter drive 2 other things. Let's say 2 other inverters. Okay, so this is totally fine. Okay, so this is A, For this guy, the input is A prime, For this guy, same thing, The input is A prime. This is perfectly fine. So this is basically so-called a multi-fan out. So basically, this is the same gate, It's connecting, it's driving the output of one gate, is driving multiple other gates. This is fine. But what we are not allowed to do, I think one of you actually asked this on Piazza, is doing something like this. So this is actually not legal. This is not a legal circuit, digital circuit. Because you look at this, So what's the signal, Is it A or B? Because both an A and B are driving the input of this inverter, So this is not legal. How do we? But in some cases, indeed, So we want to make sure that one building block is talking to multiple building blocks, or one gate is talking to multiple gates. So how do we make this kind of a choice, So basically, we know that A and B are not gonna, So we are not gonna connect to both A and B at the same time. So how do we make such choice? Okay, So that's where we need to introduce this so-called multiplexer. Okay, we actually need to insert something over here, so we can make a choice. Okay, So this is the sort of the key motivation behind having the multiplexer or Mux. So in most cases, we just say Mux. Okay, so for sure. All right, let's look at the most basic form. So this is a 2-input Mux, 2 input, 1 output Mux, and this is the symbol. We first let's just try to use the abstract notation. We have 2 inputs, I1, I0. Okay, this output Y. Okay, we are following the same convention, So we have inputs on the left-hand side, output on the right-hand side, but we need to make a choice. We actually need to select So at this moment, are we gonna use I0 or I1? So this is where we need another bit, another control bit, called S. S means select over here. Okay. So first, let's try to understand how exactly do we select, right? So with Mux, when S is 1, we select I1. Okay. See here, we are actually labeling. Okay, we associate the index. Right? We associate, in this case, integer index, right? So decimal index. So with each one of the input, okay, I1, I0. When S is 1, Y is basically connected to I1. Right? When S is 0, naturally, right, Y is disconnected from this conceptually, right? Y is disconnected from I1, but it's assigned, basically, we assign I0 to Y. That's what the mux or two input mux is doing. Is it clear? Okay. All right. So if you understand this one, you should be able to quickly understand, right, quickly parse this Boolean formula, right, this expression. So this is how we represent the mux using Boolean expression. Right? If you look at this, if we try to parse this, right? When S, right? Again, when S is 1, the first term, right, this term is canceled out, right? Right. So Y is I1. When S is 1, when S is 0, Y is I0. Okay. Any questions? Let me quickly check the chat window. So when are mux useful? Right. It's going to be more clear pretty soon. Okay. When we start using mux, but in this lecture, just treat it as right. Right. So it's like sort of like a switch, right? But over here, we actually want to make a selection, right? So we only want Y, the output, to be connected to one of the, to select one of the inputs. So this is actually related to what I just mentioned, right, in the previous slide. Okay, so in the previous, not the slide, right over here. So you want, right? So you want one gate, right, to connect to both inverters. We cannot, just directly connect the outputs of the both inverters to the input of the third inverter. It's not legal. We actually need to introduce mux. Okay. All right. So is this expression clear? Okay. If yes, then let's look at the more complex mux. Let's look at the 4 input, right? 4-to-1 mux. So we have 4 inputs over here, right? Again, let's come up with the index, right, for all these inputs, right? Again, we use the decimal numbers from 0 to 3, right? And now that we need to select from 4 inputs, we have 4 combinations, right? 4 choices. So we need 2 control bits, right, for select. Okay, we need at least 2 bits for selection. Okay, so I hope this is becoming somewhat intuitive, right? So when S1, let's say when S1 and S0 is 1, 0, can you guys guess, right? Which input do we select? I2, right? This guy, right? Because if you read it out, this is basically 2. 1, 0 is 2. Okay, essentially we just enter basically put the index, right, of the input over here for S. That's it. Okay. All right. So I already showed you, right? So for 1, 0, we are selecting I2. 0, 0, we are selecting I0. Right? 0, 1, I1, 1, 1, I3. Okay. Right. Very good question. How much asking can we have odd number of inputs? Right. Yes, we can have 3 to 1. So there we still need 2 bits. Right. We still need 2 bits. But then what happens to, since we can encode 4 combinations, right? What happened to the unused combination? That's basically a don't care, right? We can treat it as a don't care. Okay. What is the expression? What is the Boolean expression? Can you guys try to generalize from the previous one? So what is y? We are selecting from I0, right? And I1, I2, I3, right? So we add them up, right? But where does S1 and S0 come in? For the first term over here, so what is the combination? What is the Boolean expression? So how do we select I0? Like this, make sense, right? Right, many of you have already entered the correct answer, right? So basically when S1 and S0, they're both 0, right? So we get I0. And similarly, right, we can spell out, right, the rest of them over here, right? Okay. So if you look at, try to look at, right, so this expression, right, basically we have, right, 4 combinations, right, this is encoded, right? If you treat the control logic part as a separate 2 input Boolean function, right, we are basically just spelling out the midterms. That's it, right? But let's just focus on S1. Okay. So what exactly is S1 doing, right, in this case? So when S1 is a 1, okay, we are selecting this 2, right? We are selecting from this 2. Great. Otherwise, if S1 is 0, we select from this 2. Right. What is S0 doing? Any intuitive explanation? What exactly is S0 doing? Yes, right. Odd even, right? When S0 is 1, what do we select? We select either from either 1 or 3, right? This is odd, right? If S0 is 0, we select from either 0 or 2, right? This 2. Okay, right. Again, try to understand, some of the intuitive meaning of these control signals. Right. So S0 is clear now, right? So you guys are asking, right, what exactly is right? S1 doing again, right? So you look at this, if you look at these 4 input combinations, right? So we can encode them as 1 1, right? 1 0, 0 1, 0 0, right? Okay. So basically, S1 is in charge of selecting, basically correspond to the high bit, right? MSB, the most significant bit. When S1 is 1, we select from these 2, right? When S1 is 1, we select from these 2. When S1 is 0, we select from these 2. Okay, all right. So maybe let's do one more exercise, right? So just to help understand what's going on, we can actually construct even larger muxes, right? In this case, we can use this 4 input mux and 2 input mux to build the 8 input mux, right? So that's how we use this so-called building blocks, right? This is just Lego, just plain Legos, right? So in this case, we can actually have 2 different ways to organize this mux tree, right? We can in the first level we have 4 input mux, in the second level we have 2 input mux. Okay, right. So in this case, so if you look at the left-hand side, right, we use S1 and S0, right, to select between these 2 groups, right? and then we use S2 to make the final selection, right? And we can also organize it in a different way, right? We can also, have the first level. In the first level, we use a set of 2 input mux, and in the second level, we use a set of 4 to 1 mux. Right? I'll ask you guys to complete, the question marks, but maybe let's look at one of this. Okay, try to, after the class, try to figure out what exactly, right, are these question marks. But let's look at the first one. So what is the first one? Is it S1, S0, or S2? What do you think? Yeah, S2 is the high bit, right? It's S0, right? Right, because we are selecting between odd, even. Here, right? The 2 input mux, right? We are making a choice between odd and even indices. So basically the least significant bit, okay, for the input indices. So that's why we put S0 here, right? Of course, we need S2, S1, right, for making selection for the 4 input mux. I'll let you guys figure out. Right? Do we have S2, S0, or S2, S1, or S1, S2? Any questions about muxes? Okay. Right. So one more time, this is really about, right, making right. So we have many inputs to choose from, right? We're gonna just make connection to one of them at any given time. So this is where the mux becomes really useful. So actually, we can also use mux to construct Boolean functions. Oh, actually, there are more questions. Rachel's asking, so would it be different if the input were in a different order? By input, you mean S or I? Actually, the answer is yes, right? So in both cases, right? Yes, if you arrange the input in a different order, depending on what kind of order you're talking about, right? So you mean changing the indices, or you're talking about just whether you put certain things on the top or bottom? Okay, there are more questions in the stack diagram. If S0, will that apply to all the 2? Oh, good question. Steve is asking, right? So what exactly is this diagram? Indeed, right? So, so see here, so these lines are shaded, right? So basically, this indicates that the same signal is driving all the 2 to 1 muxes. Okay, right. So, but coming back to Rachel's question, it's really about the, we actually associate, right? So order does not make too much of a difference, right? It's really about the decimal index, right? For those inputs. So pay attention to the decimal index. All right. So we can also use muxes to do Boolean functions, actually. Okay. So in this case, let's say we have a 3 input, right? This is a truth table, 3 input, 1 output. Turns out that we can just implement it using a to 1 mux. Okay, like this. Right, how does this work? Let's quickly analyze this. So when A, B, C, they are, let's say 1, 0, 0, which input do we select? 4, right? 1, 0, 0, we select this input. Y will be 0. When A, B, C is 1, 0, 0. And let's just look at the truth table. 1, 0, 0 corresponds to this row, right? Same thing. So Y is 0. So essentially, what we are doing is basically, we just connect the inputs, right? For this Boolean function, right? We connect all 3 inputs with the select bits, and then we just copy paste, right? We copy the entire output column, and then connect the corresponding values with the input side of the mux, and that's it. So we can implement. So if you already have a mux, right, then we can use it to implement this Boolean function. Actually, you guys are going to be using FPGA a lot, right? Later on, although you don't need to know this, inside the FPGA, it has a lot of muxes like this to help you reprogram it. So that's actually how FPGA implement any arbitrary Boolean functions. Okay, they basically use mux, and together with some memory bits, which is something that I'm going to cover later on. Is it clear? Okay. If it's still not clear, it's basically, we are just doing the same thing, right? So this is just like truth table, how truth table work. So if 1, 1, 1, right? So we select 7, right? Which correspond to this row, right? So this specific output element in the output column, this row, and this is the one, right? The output column corresponds to the input side for the mux. Okay, so this is pretty useful to understand, right? Actually, there will be a quiz about this specific property of the mux, right? So make sure you guys ask questions if this is not clear. And the quiz is going to come up pretty soon in 1 or 2 slides. All right. Over here, we can use a input mux, right, to implement a 3-input Boolean function, right? Because 8, right? So this is 2. A is 2 to the 3. Turns out that we can actually do some. There are some techniques that we can use to reduce the complexity of the mux. Turns out that in most cases, actually, we can get away in a cheap way by, for example, we have a 4-input function here, right? This is a 4-input, 1-output truth table. So if you look at the previous slide, we actually need a 16 to 1 mux, right? To copy the entire output column. So we need 16 inputs. But turns out that we can actually get away with 8 to 1 mux, a simpler mux, by adding some additional logic like inverter. Okay, so let's try to make sense of this, right? So how do we actually do this? There will be a quiz right after the slide, so pay attention. Okay, let's say we only have 3, so 8 to 1 mux, right? So we only have 3 input bits. Let's put ABC here, right? 3 control bits, 3 select bits. So we cannot use all 4 inputs, right? But let's just say we put ABC here. So when ABC, okay, they are all 0. Okay, so which part should we focus on in the truth table? So what should be the output, right, for Y? You want to implement this truth table. We look at these 2 rows, right? This is where ABCs are all 0, right? But if you look at these 2 rows, right? So it actually doesn't really matter whether D is a 0 or 1, right? So regardless, Y is going to be 1. So that means first for mux, right? So if A, B is all 0, we're going to select this input, right? I0. And if Y is going to be always 1, regardless of the value of D, then we put a 1 here. Make sense? Right? How about 0, 0, 1? What do we connect to I1? We focus on the next 2 rows, right? These 2 rows. So again, interesting in this case, right? So we don't really, right? We don't really need D. So this is a 0, right? We can keep doing this, right? Let me clear this. So hope this is clear. Clear this. We basically select n minus 1 inputs, right? In this case, we put ABC here, right? You guys already agree, right? So for most inputs, it's actually pretty straightforward, right? We can put the constant value there. But let's look at 3, I3. I3 is where ABC is 0, 1, 1, right? The corresponding control bits or select bits. So they are 0, 1, 1. So 0, 1, 1 is where? So this is right. correspond to these two rows. In this case, indeed, right? So Y also depends on D, right? So what do we put? What do we connect to? I3. Yes, right? Very good. So just D, right? Okay, in this case, just D. Because you know, Y for this specific input, right? For I3, okay, for this specific two rows, Y agrees with D. So we just put D here. How about this one? How about I5? Right, D not, right? So Y disagree with D, right? And so they are opposite.